Buenos días a todos y a todas. Es para nosotros un gusto tener el día de hoy al doctor Marc Ballouz, presidente de la Sociedad Internacional de Mecánica, Suelos e Ingeniería Geotécnica. El día de hoy él viene a ofrecernos una conferencia cuyo título es Geotechnical Marriage Between Theory and Practice. Welcome, Dr. Marc Ballouz, to Mexico, to our university, to our institute. It's a great honor to have your presence here. Okay. Tenemos el honor de contar con un par de invitados especiales. Contamos con el ingeniero Walter Paniagua, vicepresidente por Norteamérica de la Sociedad Internacional de Mecánica de Suelos e Ingeniería Geotécnica, y contamos con la presencia de la ingeniera Daniela Pollack, expresidente de la Sociedad Chilena de Geotecnia y actual presidenta del comité organizador del 17º Congreso Panamericano de Ingeniería Geotécnica. Muchas gracias. Cedo la palabra al ingeniero Walter Paniagua, quien nos presentará una breve semblanza del doctor Marc Ballouz.
Muchas gracias a la doctora Alexandra Ausa por recibirnos aquí en el Instituto de Ingeniería de la UNAM. Y bueno, para mí es un honor y un privilegio presentar a mi amigo y colega Marc Ballouz, originario de Líbano, que obtuvo su licenciatura en Ingeniería Civil por la Universidad Americana de Beirut. Posteriormente trabajó ahí mismo en Líbano 2 años antes de cursar estudios de posgrado en la Universidad de Texas A&M, donde obtuvo su título de maestría y de doctorado bajo dirección de Jean-Louis Briot, otro buen amigo de nosotros. Posteriormente trabajó como consultor en la ciudad de Houston, en el estado de Texas, en Estados Unidos, antes de regresar al Líbano para fundar su propia empresa, que se llama el Instituto de Geotecnia y Materiales, en 1997. Como profesional, desarrolló un interés particular por las cimentaciones profundas en condiciones de suelos difíciles para estructuras especiales. También siguió trabajando en el ámbito académico, impartiendo cursos de mecánica de suelos e ingeniería de cimentaciones en la Universidad Americana de Líbano, la Universidad de Notre Dame y la Universidad de Líbano. Sigue publicando artículos técnicos sobre cimentaciones profundas, deslizamientos y geotecnia en general. El doctor Marc Ballouz ha sido muy activo en la Sociedad Internacional de Mecánica de Suelos e Ingeniería Geotécnica. Fue vicepresidente del Comité de Innovación y Desarrollo y líder del Comité de Relaciones Públicas de esta misma asociación, donde yo tuve la fortuna de participar con él. Fue parte de la Junta Directiva de la Sociedad Internacional de 2009 a 2017 y actualmente es el presidente. Marc, the floor is yours. Welcome.
Thank you so much. It's an honor to be here, such a pleasure. Thank you, Dr. Alexandra, Dr. Walter, and Dr. Daniela, where is she? Oh, here you are. You should be in the front seat. You know, I live just a few hours from here by plane in Texas, and it's the first time I visit Mexico City. I'm so ashamed of myself. Finally, I got this invitation. Thank you, Walter, a second time. I'm so happy to present this lecture, and I'm so happy to see many young students and engineers, because this lecture is basically a review of my life as a geotechnical engineer, starting with the fundamentals, and then few case histories where I had to go back to the theory to solve the engineering problems. I will not talk too much, and I will start. Hopefully this is working. So it's nice to be in Mexico City, and this is a picture that Walter sent it to me, and I loved it. And now you have a friend from Lebanese origin. The presentation outline, I will tell you a little bit about the family of ISSMGE, the society that I am leading, and then we will talk about the rest of the presentation, which will be the marriage between theory and practice in geotech. The ISSMGE, or the International Society for Soil Mechanics and Geotechnical Engineering, was founded in 1936. And the founder was the father of modern geotechnics, Carl Terzaghi. I'm sure you heard of him if you are a geotechnical engineer. We represent 90 countries. So it's a society of members, of country members. So we have 90 members, and each member is the national society of that country. I will go back here. You have to help me, mainly Daniela and Walter, to fill up the white countries to become red. So in red, you see the countries that are already members of ISSMGE. The structure of the society, at the top you have the council with 90 countries. In the middle is the board with 12 members. And you can see here that 3 of the board members, 3 out of 12 are in this room. So this is a great lecture. It's the first time where we meet so many board members. And I have to note that Professor Neil Taylor is the Secretary General, has been serving for more than 20 years and is giving his place this coming summer to a new secretary that we have to elect very soon. This is a picture of the board during the elections in Sydney, Australia. This is a closer picture. And you can see here the Vice President of North America and the appointed board member, Daniela. They are both here with us. And this is a great honor. Thank you. The main horse driving all this are the technical committees. There are about 40 of them or more. And each one of you can participate in those technical committees if you talk to Walter. Please connect with issmge.org. And I have to mention the corporate associates. These are the companies that are supporting the society besides the countries. And if you are working in a company and the logo is not here, make sure you become member of our society. My job is to make this page full of logos. Also, for the young especially, please connect to the virtual university. We have about hundreds of webinars and seminars and lectures that are free, open access. And I'm sure you can find a subject that is of interest to you. Another thing you should note, if you write a paper, please publish it in our International Journal of Case Histories. Also, hundreds of papers, free access to all the students and engineers and anyone who likes to visit the site. Another thing is the GeoWorld. If you don't have an account, open an account with GeoWorld. It represents the Facebook of geotechnical engineers in the world. It has many features, even a map with all the geotechnical located on this map. I was surprised one time to find a neighbor who's a geotech in Texas using this map. This is mygeoworld.com here at the top. Is what you should connect to. The foundation, I have to mention, since many students are here, if you're feeling like going to a conference, especially abroad, don't hesitate to apply for money and support using the application form on the website. The foundation, the ISSMGE Foundation, is there to support young engineers like you. Finally, a theory that is going to launch this presentation. If you are in love, you have to go dig deep into the soul and the heart. And if you want to understand soil, you have to also dig deep So, for me, soil is love. Yes, it's fun to be here. Let's do the serious stuff. Not very serious. I will entertain you a little bit. Geotech engineering life. I will start with the fundamentals. I will be a little bit slow at the beginning, but it's very important because I've seen so many people, consultants especially, jumping onto Plaxis or software before they think. We are engineers, we are not machines. These are some pictures from when I was at your age. I'm looking at the young. At the bottom right here, you can recognize our friend, mutual friend, Professor Jean-Louis Briot, who was a previous president of ISSMGE. Here, I'm on a quarry studying the rock face, here in school. And I put this picture to show you that you always marry theory with practice. Here we were doing, with a pressure meter, oil pressure meter, studying the anisotropy of the soil in a tunnel to see the squeezing of the tunnel, if it is symmetrical or not. I will skip to start something very, very important. And really, this is the most important slide of the entire presentation. If you want, take a picture of it. Solje is a word I invented because so many times you get people asking you questions, engineering questions, and you jump out of excitement to give an answer. Never do that. Always collect the data. Ask first for the soil report. Ask what loads are we expecting? Is it lateral load, horizontal load, earthquake load? The geometry, talk to the architect. And very important, the history. Was there a failure here before? The old people are telling you there was a water source of some sort, an old lake like Mexico City. That's why you have many problems here. And always, always visit the site. As a forensic expert, they send me reports and I evaluate, and on the airplane I have a solution. I get to the site, to the country, I visit the site. I would say 80% of the time, after I see the site, I change my mind and change the solution and change the recommendations. So always visit the site. The mode, if you can detect what is the mode of failure, what are the theories applied, which software should I acquire and start working, you solve the problem. Doing the actual calculation is not that important. The mind is the most important part. Please always keep safety at the top of the tripod, which is the most stable solution. So here, you can find a foreman to build a bridge for you, but it will definitely be very costly or unsafe. That's why you study engineering. And it has to also look at functionality. Very important slide. The units, compatibility of units. If you cross the border, they talk in feet and inches, and you are just 1 kilometer away on the borders. This is so funny. And I had a problem with a building, brand new building, a headquarters of a law office that was sinking 1 millimeter per day. In Nigeria, 1 millimeter per day, can you imagine? And there were a big company rushing, doing micropiles to stop it. And the problem, after I reviewed everything, was that the structural engineer gave the loads in tons, and the consultant designing the foundation never used tons, used kilonewtons. So never ever give answers without units. These are my children. So 10 milliliters, yes, I was young. And they were young too, now they're your age. 10 milliliters of antibiotics can save a child's life, but 10 liters can really kill an elephant. So remember, units. I will jump to living engineering, to the simple problem of walking onto sand. If I want to collect Solji, so every problem, even this, you do the soil, the load, the geometry. The geometry is about 230 centimeters square. The pressure, so male and female, about 3 tons per square meters. The history, note here that the female has sunk or is settlement more than the male. Interesting. So definitely you can say that the settlement is not related to the load or the weight, it's related to the pressure or the stress. So you have to live your engineering, keep observing what's happening. Let's apply the simplest form of Terzagh's equation that we all know, I hope. So here in this case, 0 for cohesion, 0 for being on the surface. You get ultimate bearing capacity of 0.1 kilogram per centimeter square. However, you are applying 0.3 kilogram per centimeter square. So you should expect failure. You're 3 times more than the ultimate. But what happened? Is this a really failure or what's happening? So in this case, because it's sand, you sink. And as you sink, if you look at the second term, the 0 becomes with a value because you are going deep in centimeters. So it's picking up, this number will start going up and then you reach equilibrium. I will not elaborate too much. It's a simple equation. It's a philosophical thing to keep going by saying, actually, you're walking in the wet area. So you have some cementation from adhesion of the apparent cohesion. So if we do the math again, this time the cohesion that is letting us build sand castles is pretty high compared to the other terms, and now for sure you don't have a failure. So there is a large effect of suction. But what if we go to the dry sand area? And let's play with the equation, and I want to tell you why we are playing with the equation. We are playing with the equation by setting the settlement as a variable, and we're trying to detect using the bearing capacity equation. If you put S as the unknown, you get that you sink in dry sand 5 centimeters, which is logical, right? I'm sure you tried it. So I will jump to deep foundations now. With deep foundation, let's say SPT on the sandy beach, average in the few meters 8, standard penetration test. This will give us a friction between the pile and the soil of 2 tons per square meter. And I want to ask you a question. What is the force needed to lift you off and out of this agony or this situation? I will tell you a story of my dad, who is a civil engineer since 1954, and I think he's watching us from Lebanon. One time he receives a phone call, and he's in his office. Remember, at the time, no cell phone. Barely those phones that you don't remember, but we do. So he picks up and they tell him there is a failure in the trench. They are building a big sewage line in the major city north of Beirut. He said, don't do anything, I'm rushing there. And he jumped in his car, no cell phones, and as he's driving, one of the workers was buried up to here. His brother is a driver operator of a big backhoe excavator. The brother was so excited to save his brother. So he turns the backhoe and put a ropes behind his brother's underarms. and pulls with the excavator. And I'm not going to tell you what happens. But you can figure it out by doing the math. Always go back to theory. If you do the math, and uplift is only friction, you get 720 kilograms needed, and only you're buried to the knees. So you can die and split in half. And that's why in this picture you see professional rescue teams. This is a picture in Boston, USA. Look how they clear way below the knee before they lift with the harness. Another interesting question where intuition may fool you, never rely on intuition. If I take a rope, the red rope, and throw it around the earth, all around, and then I make this rope 6 meters longer, and I grab the two edges of this rope and make evenly spaced all around the world. And the question is, how high will the rope rise? Most of you, like me, answered quickly, it's negligible. Imagine 6 meters more around the earth. But this is not true. Look at how simple we can go back to 2 pi r and find that it will rise 1 meter above ground. Always go back to theory. These are equations that change the world. I need to drink. Engineering. There is always atmospheric pressure around us, right? Sorry, I need a minute. There is always centrifugal force, right? Let's see if this one we need some prayers. Alessandra, don't worry, I'll do it. Let's see. It's not going to work. It's very risky. The atmospheric pressure is stronger than the shell. When you fail, what do? You try again? Yes, you need a glass. I use these to keep my jacket straight. So many of you, let's see if it works here. Sum of moments, sum of forces around 1 point are all zero, right? 6 equilibrium equation. If I bring another external force, it's earthquake, and then failure. And when it fails, don't touch it. It's stable, same like a landslide. Yes. So if it fails, we don't touch it. We go back to theory, make sure we have a safe solution, and then we start working to fix it. I will move forward. These are 2 equations that changed my life. And this is a picture, I don't know if he can see us, but this is my father in 1958 installing water supply and distribution in a deep valley in Lebanon. We have high mountains like here. I think the highest peak here is like 5,000 meters. We have 3,300 in Lebanon, but we have snow because we are higher in latitude. This is me, same area, going to check what my father did 50 years ago. Case histories, now we're starting some experience. I have 5 cases, I don't know how much time we have, and each one has some importance to it. I will try to cover as many as we can. I don't know if you can control the time, let me know, Walter. This first one is an old, not old, is a new hotel that was left during the Lebanese war, civil war. And then when the war ended after 15 years, so the war started 1975, and then reconstruction of Lebanon after the peacemaking in 1990. So this was in 97 project. The new client wanted to demolish this building and build a new one. So they did implosion, and you can see it. My job, if you look here, the blue represent the basements, 3 basements underneath the building. My job was to install anchorage to maintain equilibrium of the infrastructure around and the roads around. I don't know if the video will play. Yes. I don't know, can you hear the explosions? So as the building is collapsing, my heart was beating because I was doing the opposite, maintaining equilibrium. And the main, and you can see me here rushing as soon as the explosion finished to see what happened. Keep an eye on the tower here because it has a big thing to say. Go back to Solji. So to design those anchors, I did the soil investigation, but the main problem here was the load, because the load was of course coming from the side. As you can see here, the earth pressure, water pressure, live load pressure, and we had some infrastructure here. But the main problem was what happens as all this load is collapsing dynamically and hitting the earth and coming back to us as a wave and pushing as extra acceleration onto the lateral fold. That's what I needed to design those anchors. And to do that, I had to go back to history. Historically, there was the same situation of a building nearby, slightly smaller building. So I took the data, the time data of the geophones, and so the history was my main thing that I used. And I had to go back to do the Fourier series. And by using the discrete form of the Fourier transforms, I was able to develop in the frequency domain both the vertical acceleration spectrum and the horizontal acceleration spectrum. By doing so, I got the maximum acceleration peak. I even multiplied it a little bit more because remember, this is coming from a building that is smaller. So I feel confident, and I used my engineering judgment. And that's where I designed the anchors using the old Rideau software. Keep an eye on the deformation predicted. And this is the 3 basements will look like this. Water table is here. This is the bottom of the basement, lowest mat foundation, and this is the road level. And here you can see the 2 anchors that I designed. And I'm gonna skip here. This is the details of the design using software we developed in-house, design of structural analysis to make sure the structure doesn't collapse. And these are pictures that Walter would like. The 3 micropiling machine drilling together for the anchors. And the anchor installation, you need the mixer and the high pressure grouting pumps. We used Clivio Italian pumps, I'm sure you heard of them. And the most important slide of this is this one, where I had to use my imagination and create an anchor block that does not collapse under high shaking. What we did is simple, put old or pieces of truck tires before we tension the cables. And if you look at the wedges, the conical wedges, if you know how to install anchors, you pull the cable, you insert the wedges, the cones gets locked. But the fear was during under high shaking that these will pop out. So the cables are here, we put tubes and we welded those tubes at the tip. So these tubes will act as extra push on the clamps. And the nice thing about it, if you want to go back and retension them, you can cut here, remove the tubes and retension the anchor. So it's kind of redundant system. More pictures of the collapse. So this is stage 1, stage 2, and stage C, the final product. When I saw this, I was happy and I got paid. So this is the stable empty box. What happened? Now, remember this shape. This is the prediction. But if you look at the Magenta curve, is what we measured from the inclinometer. These are the lines of the inclinometer at different dates. And this one is after the explosion. And first I said, wow, how far am I? That's crazy. So you go from 3 centimeters in one direction to 3 centimeters in the other direction, and you call yourself engineer. I was so ashamed of myself at the beginning. But then when I started looking at the details, you have the anchors pulling and also that tower that did not get destroyed fully. It came down and hit with high force the edge of the slab, the edge of the wall, and pushed in passive form the upper layer of the soil. And that's why you have in the top 3 meters this deformation. So what can you say? Is it a bad design? I don't think so. We designed for the worst case scenario. We were lucky here that at the location of the inclinometer, we had the tower pushing in the positive direction. And this is the birth of the new height regency in Beirut. Between each case history, I will give you a nice picture of my home country. These are the cedars of Lebanon, and the cedar tree is the only vegetation that can live above 2,000-meter altitude, and that's why you see it on the Lebanese flag. It represents strength, power, and life in difficult conditions. Second case is also something you like, because during our discussion yesterday, I learned that Mexico City has a lot of deep shoring projects and facing deep shoring problems. And I want to tell you something here. If you have a new building or an old one, old structure, which one you worry about? I mean, the one to the right, much higher loads, and the one to the left, only 2 stories. I tell you that, I'm sure Walter knows, that the building to the left has no tensile elements to keep it together. and is more dangerous. And this is another picture to prove what I'm saying. You can see that the foundation is totally, from this landslide, totally exposed, and the tower is still vertical. Why? Because of all these tensile elements. Together, it becomes a block, and only when the center of gravity is outside the touching area is when it will fall. And the same will happen with high-rise buildings. So if I'm cutting next to a high-rise building, I worry, of course, I design, of course, but not too much from experience. I have a webinar regarding challenges ensuring deep excavation. Again, visit ISSMGE website. This is the start, launching on the project. I will skip fast here. If you look, we have different sides. So this is design of one side in yellow. This is another side. And this is the third side, similar sides. And this is the side that gave us problems here. And this is the curve that we predicted, theoretical curve. And look what happened. After 3 rows of anchors and reaching 13 meters, we started seeing problems with the neighboring building. And look at the change in the theoretical prediction and the actual measurement. About 1.5 centimeter difference between these two curves. Around this area, there was a water source that nobody detected or knew about. And in the neighboring buildings had cracks. And we started measuring those cracks. And we had to bring back backfill. And that was the fastest way to stabilize that side. And go back to a new solution. Strengthen it with struts. That was the fastest way. Sorry. And this is the product. And when we did that, of course, we put some compression into it. This is called active system, like the anchors. You activate, you pull, you put pressure, so you have reduction in movement next door. And that's the final product of the Trabot towers. This is the building that was cracking. Again, we had to go back to theory and redesign before we are safe. The importance here is the importance of field monitoring. Now it's kind of mandatory everywhere you do excavation. You have to monitor all the surrounding and all the structures around you. Another picture of Beirut. So we're changing case history. You can see the mountains here at the top, Mount Sanin. This time the Versace Tower was a problem of either we go with deep foundation or we invent another system, which is grouting, because the soil had cavities in it, like you see here. It was detected during investigation. The consultant didn't want to take a risk, so he said we put piles. But the soil was marly, so pretty strong soil. And I discovered that this is too expensive. So what we did is we studied the pressure on the mat, and where the red zone of the pressure was higher than the spoil we removed. If you remember the floating foundation principle, when you excavate, you're removing stresses anyways. So if you put less stress, you don't have settlement. So we did three sequences of grouting, and you can see here, I like this picture, you can see from different holes when you're grouting on one, how the water is jumping from the other holes. So these cavities are interconnected. We take measurements of the velocity of the penetration, the pressure of the drilling, and we develop a system where for each grouting hole, we can tell if there are holes or cavities or not. And we develop those tables. I'm going fast, I know, but this is what I want. So here, you can detect when you are below this line that you have a cavity. From here to here, a cavity, from here to here, possible crack. And that's why you do, with this theory, you come back and pressurize again and again, 2 times or 3 times, to make sure you no longer have anything below the red line, which is a typical value of 20. What I want to show you is this. I don't know if the video is playing. Anyways, it's not playing. But in 3D, you can see how those theoretical cavities can be connected together. And after grouting, we ensured that there are no more cavities with the theory I showed you, and we saved about $1 million from the piling foundation they had for the Versace Tower that you see here in Zaytuna Bay. Sea breeze, and this, I think I'll stop after this one and give you the conclusion. Are you okay? Are you happy with the presentation? I don't want you to be bored. This one is a wind farm here nearby in Texas. It's about 174 turbines delivering 400 megawatt power plant. We go back to Solji always. So we're getting the soil data, CPT, SPT, whatever you can get your hands on. And then you look at the geometry. We have the diameter of the turbine, 101 meters, 120 meters high. How much does Mexico do of these turbines in terms of renewable %? Did they start building large wind farms? Nice. It is the future. And solar. Looking at the loads, so Solji, you have the loads. I summarize the loads under different conditions: emergency braking, lateral high gust winds, the vertical load, and we design for these. Maximum moment, and in what type of foundation should we put? Shallow foundation. Besides the gusty wind, we have to worry about surge waves, like small tsunamis coming from the tornadoes in the Gulf of Mexico. And when you do that, you worry about scour underneath the footing. So shallow foundation, even though you can build it big, was a no-no for me. So we opted for deep foundation system. And when we did that, I have to go back to the fundamentals. If you remember, the vertical load affects the lower layers of the soil. The lateral loads affect the upper layer. And it's only in this case that you can add them together in such problems, because the layers of soil are not related to each other, and soil is not elastic. So theoretically, you cannot do that. But because there are different soil in the problem, we allow ourselves to cheat. When we study lateral loaded piles, I don't know if any of you took this course, but we developed the transfer length number L0. And if the length of the pile is less than L0, we use the rigid theory. And if L is more than 3L0, we use the flexible theory. And L0 is related to fourth root of E, modulus of the pile, I of the pile, and the spring modulus of the soil. So it's an interactive value transfer length. I will demonstrate now for you what I mean. You may want to take a picture of this. Design-wise, we don't want the upper deformation to be more than 2 centimeters, but also the angle, Y prime, you don't want it more than 2 degrees for the turbine, and the maximum moment should not break the pile, at the pile body. Go back to the theory. That was my PhD dissertation. We developed the equilibrium equation of discrete elements, kind of PY, but with a dashpot under dynamic loading. And I'm giving you here some typical values for the modulus of the soil, for clay and for sand. And when you do that, the equation, I reached the solution of y as a function of z, the depth, and time is from here to the Ferrari about 33 meter long. 33 meter long, font 16. So we can go around this. And this is what the software is calculating at every step. Before, in the past, without the software and the computers, we couldn't do that. So that was the solution. And here's on one of my job sites, I made the guys carry the solution equation so they feel what they're doing. I hope this works. You will see the pile wobbling, and it's in a flexible form. Can you play it from? Yes. So at a certain frequency of the turbine, as the turbine is turning, this is what the pile is doing. And you study the maximum moment, maximum deformation, and you put an extra safety factor on that. What we discovered with this equation is that the missing link, you cannot interpolate between the two, like the teacher used to tell us. And we discovered with the demonstration, can you play this video, please? What I'm talking about if you take any element in your hand and imagine this is the pile embedded in the soil, and this is the upper turbine, and you put load on it, your fingers are your finite element, software, discrete element. A nice lady will not be able to bend the pile because her hands are soft soil. And the pile will behave as a rigid pile. The same pile in strong hands can bend as a flexible and behaves as flexible. And this theory, if you look, is it plain? The dash, as we change with the variables, the red dash line is the new theory. The blue is a rigid theory, and the green is a flexible theory. If you go scroll up to here, can you see up to here with the You see the arrow? Yeah, it's okay, we can skip. It's not playing, is it? It's okay. This is the same demonstration I showed you. So if I put a straw in sand or in mayonnaise, this becomes rigid, this becomes flexible. With the new theory, we were able to solve what happens in between. That was the importance of that theory. And if we play the dynamic equation at low frequency, it matches the static solution. I will jump now fast to, this is the solution of in 3D using group software. I'm sure you used it, Walter. I like this software. And that was a solution for the sea breeze that is being built very soon. Nicest caves in Lebanon and probably in the world, the Jaita caves. If you ever visit Lebanon, you have to go in this. And there are small boats that take you on a tour. I will skip this one because too much time. Well, maybe I'll show you just one slide. On this project, it was in Manhattan, New York. I was called because the city of Manhattan stopped the works because the neighboring the project was here, and the neighbors, as they started working, started moving, as you see in this picture. And the top moved around P8, point P8, 3.8 inches. There are advantages to monitoring, but also the engineer got panic and they stopped the project and went to the city. And they didn't know what to do. And they called me, and when they called me, all I had to do is collect the data. It's amazing how so many engineers on this project did not collect the data, put it together, because the monitoring people did not talk to the consultant, and the consultant did not talk to the site engineer. But if you put it together, it became obvious to me, and look at these movements at different points, the curves, and in yellow was from the site report, and we discovered that when they were doing secant pile, we had a big jump. When they were doing sheet piling with vibration, we had a big jump. And when they were doing down the hole hammering, we had a small jump. So what I did is I stopped secant pile methodology that they were doing and changed it. And we stopped the sheet piling vibration, and the problem was solved with zero investment compared to the client was about to pay $1 million in high struts and mic underpinning, and it was crazy. And I was able to convince the city of Manhattan that we will be safe. Of course, we did some dynamic simulation to see what happens if we keep going and make sure we stay within the limits. This is up to here is what happened. And then here is what will happen once we finish the excavation and we install the strut. I had to add a strut system. So you always go back to the theory. I will jump fast. These are the structural simulation. Make sure that the building is still safe despite that it moved 3.4 inches from the top. And we detected that it can move up to 7 inches without any problems. Reaching the conclusions. I see many of you already tired. Me too. This is the Holy Valley of the Pshare Valley in Lebanon, or the Kadisha Valley. Many of you don't know, but Lebanon is the only Arab country governed by a Catholic president. Jumping to business as engineers, take a look at this. It's a saying by Butler in 1931, and I really like it to be from the top that make things happen. Already from you being here at a very honorable university is gonna get you there. Be ready to be international means if you are working in Mexico, remember that we have permafrost in Canada, and if you're in Japan, you can be from hot to cold in the same country, and you have to be ready to work anywhere around the world nowadays. The whole world is interconnected with internet, Facebook, Instagram. You cannot say, oh, I'm gonna work only in Mexico. This is not gonna work. And be ready also to be international. This is the corruption map. I know you are in red, but so are many other countries. So maybe corruption is normal, I don't know. I'm used to it coming from Lebanon, working in Nigeria, but I'm also used to doing nice deals in America and in Europe. Be ready for anything above the table or under the table deals. I see Daniela laughing. Chile is red, right? No? Oh, it's yellow. Congratulations. Nice. I like that. Japan is very light, light yellow. And you go to jail and you never come out if you play. Final conclusions. Lessons learned. One slide. I promise you we're near the end. You may want to take a picture of this. Collect Solgi, like we said. Don't mess with the units. Don't rely on intuition. Always check the theory. Make sure you use all the theories made available, all the data made available, SPT, CPT, DMT, pressure meter, borehole shear device, whatever you can get your hand on, and use all the theories you can do. Plaxis by hand. I like the by hand to get the simple first estimate. Always do by hand. I always do by hand first. Don't limit yourself to the code because the code does not cover all the problems. Always check it and don't compromise safety if you do your own design. Conduct monitoring and long-term observation. Visit the site, call the client, ask him how is the project doing. This will help you with your continuing education. And be ready to expand that internationally and stay connected to us, your ISSMGE family. We are here for you. And finally, I like this saying by Steve Jobs. The only way to do great work is to love what you do. Thank you. If you want question, answers. Everything was clear, perfect. Thank you so much.
Gracias. Thank you.
I made a mess.
Yeah. Thank you, Dr. Ballouz, for your presentation. We have you visit Mexico soon, and I promise have a glass of water.
Solid glass.
A solid.
We'll do it in Guadalajara.
Yeah.
Everybody is following to
Invitamos a los que van a ir a Guadalajara a presenciar el truco, pero en vaso de vidrio, porque estaba preparado así. Bueno. Bueno, pues muchas gracias a todos los asistentes. ¿Alguna pregunta? Bueno, muchas gracias por su asistencia. Muchas gracias de nuevo. Gracias, thank you, Dr. Ballouz, for your presentation. Nos vemos entonces. Mucho gusto.
This one.